Good morning. Welcome to the class. Today's class we are going to start the unit 3, that is second law of thermodynamics. Already we completed the unit 2, first law of thermodynamics. First law of thermodynamics can be applied for a cycle. For a cycle, first law is given as cyclic integral of Q is equal to cyclic integral W. And first law can be applied for a non-flow process. For non-flow process, first law is given as Q is equal to W plus del U. And first law can be applied for a flow process. For a flow process, first law is given as Q minus W equal to change in energy. So this is according to the first law, and the first law statement can be given as energy neither be created nor be destroyed, and energy can be transferred from one form to another form. Now we will go to the second law. So in order to go for second law, there are some restrictions are found in the first law. The restrictions on the first law, that are the limitations of a first law, are given us in terms of 2 points. The first point is, according to the first law, work and energy are mutually convertible one into another. Work and energy are mutually convertible one into another. This is the first limitation. And the second limitation is, first law does not impose any restriction on the direction of energy transfer. That is, either from the heat to work or heat to work to energy, work to heat, there is no restrictions are given by the first law. So these are the two restrictions. So let us discuss these 2 points by means of some fewer examples. So first example, we can take the milk on a body. So when we take a milk on a cup, the cup is having some hot temperature and the milk is also having some hot temperature, and there is a transfer of heat from the milk to the surrounding is possible. So this is according to first law, it is okay. But in the reverse side, when there is a higher temperature or some temperature outside the milk, or when the milk is in warmer condition and the environment is in hotter condition, is it possible to transfer a heat from a surrounding to the milk? That is not possible. So here the mutually convertible of heat into work and work into heat is not possible, and here the direction of flow is also not possible. So let us take one more example. When we take a heating element, so when we put a electrical heating element in the switchboard, when we switch on the electrical energy, there is a electrical energy is converted into heat energy. And on the reverse side, according to the first law, the transfer of heat energy into electric energy is not possible. So this is not this is also violates the first law of thermodynamics. Then we will take one more example of braking system of an automobile. In a braking system of an automobile, there is a transfer of kinetic energy into heat energy. So the vehicle is moving in a road. When we are putting the brake, the kinetic energy of the vehicle is transferred into the heat energy, in the brake. But the reversal in this case, that is, when there is a heat energy is produced on the braking system, is it possible to convert it into kinetic energy on the vehicle? So this is also not possible. So these 3 cases, the hot milk and the electrical heating element and the braking system of an automobile, when we analyze these 3 things, it is very clear that these 2 restrictions of first law is possible. So once again I am repeating restrictions or limitations of the first law. So first limitations of the first law is work and heat are mutually convertible. This is according to the first law, but it is not possible. So this is the first limitation. And the second limitation is, first law does not impose any restriction on the direction of flow of energy. So flow of energy either from heat to work and work to heat is possible according to first law, but it is not also possible according to the real conditions. So there are few restrictions on the first law. That is why there is one more law is required. That is why we have a second law of thermodynamics. And in second law of thermodynamics, we have 2 statements. Let us write the 2 statements first. So second law statements. So second law statements. So first statement is given as Kelvin Planck statement. And the second statement is given as Clausius statement. Somehow we discussed about a few previous laws. So first let us take the 0th law of thermodynamics. In 0th law of thermodynamics, it defines the equilibrium and temperature. So we can measure temperature or we can define the equilibrium by means of 0th law. And first law, we can define the heat transfer, work transfer as well as energy transfers according to the first law. So these are restricted to these only. Now let us take the second law statements. First let us discuss the Kelvin Planck statement. So according to the Kelvin Planck statement, it is impossible to construct an engine working in a cycle which transfers the heat energy into equivalent amount of work. This is the statement according to the Kelvin Planck. So according to this statement, we cannot derive an engine which converts the heat given to it into 100% work output. So this is impossible. So we need a device which is possible, which converts some amount of heat into work and rejects some heat to the another body. This is the only possible thing according to the Kelvin Planck statement. Now let us go to the Clausius statement. According to the Clausius statement, it is impossible to construct a device to transfer the heat from a lower temperature reservoir to the higher temperature reservoir without any heat, without any work input. So according to Clausius statement, when we transfer a heat from a lower temperature body to higher temperature body, it is possible, but according to real condition, it is not possible. So this is given by Clausius statement. So these two statements can be explained by some other devices. So first let us define some of the terms related to the second law of thermodynamics. So now let us write the terms. So terms related to second law. So first we have to define thermal reservoir. Second one is we have to define heat engine. Third one is we have to define refrigerator. Fourth one is we can define heat pump. Fifth one is we can define efficiency of the heat engine, and sixth one is we can define COP of the refrigerator or heat pump. So we have to define all these terms in order to get a clear idea about the second law of thermodynamics statements. So first let us define the thermal reservoir. Thermal reservoir is a hypothetical body which is maintained at higher temperature, and when we give some heat to the thermal reservoir or when we take some heat from the thermal reservoir, the condition of the thermal reservoir will not change. When we take some 1000 or 10,000 joules of energy from a thermal reservoir, or when we give some 1000 or 10,000 joules to the thermal reservoir, the temperature of the thermal reservoir will not change. This kind of machine is called thermal reservoir. So here we have a real-time examples of ocean. So when we take some energy from the ocean or when we give some energy to the ocean, the energy condition of the ocean will not be changing. We have a river. So when we take some energy from river or when we give some energy to the river, the condition of the river will not be changing. Or otherwise we can take the world. World is an example for a thermal reservoir. So there are lot of refrigeration systems are running in the world. The refrigeration systems are giving some heat to the atmosphere, but there is no change in the condition of the atmosphere. So it is an example for a thermal reservoir. So second term is heat engine. Heat engine is a device which is converting heat into work output, and some heat is rejected to the low temperature reservoir. So this kind of device is called heat engine. Heat engine receives some input, heat input from some reservoir and converts some amount to work and rejects some amount to the some other reservoir. This is called a heat engine. And the third one is refrigerator. Refrigerator is a device operating in a cycle which is maintaining the body at lowest temperature other than the surrounding. So we have a refrigeration system, we have a refrigerator or air conditioner in our human life. In a refrigerator, the body of the refrigerator is maintained at lower temperature than the surrounding. So it is always removing some heat from the refrigeration system. So this kind of thing is called refrigerator. The next one is heat pump. Heat pump is a device working in a cyclic process. It is always maintaining the space at higher temperature than the surrounding. So heat pump is a device. For example, in a winter condition, we are switching on the heat pump in our room. So the room is getting higher heat than the surrounding. So it is receiving some heat from the atmosphere which is at lower temperature, and that heat is given to the room. So the room temperature is maintained at higher value. So this kind of device is called heat pump. And the next one is we have a efficiency of a heat engine. So we can simply define the efficiency of the heat engine is the ratio between the work produced to the heat input given to the heat engine. So eta He is equal to the WE by heat supplied to the engine. And the last one is COP. COP is nothing but the coefficient of performance. So coefficient of performance is the other term for efficiency. For refrigerator and heat pump, we can use this term coefficient of performance. COP of the refrigerator is nothing but the how much refrigeration effect is obtained in a refrigerator to the how much work input is given. So the COP of the refrigerator equal to refrigeration effect divided by work input. Similarly, COP of the heat pump is given as COP of the heat pump is equal to heat supplied divided by work input to the heat pump. So these are some definition terms we must use in a second law of thermodynamics. Now we will go to the explanation for the second law of thermodynamics. That is, we will go to the first statement, Kelvin-Planck statement. Kelvin-Planck statement. So according to the Kelvin-Planck statement, it is impossible to construct a heat engine. It is impossible to construct a heat engine working in a cyclic process and receives the heat input from the high temperature reservoir and transfer it into the equivalent amount of work output, HE, we can call it as work output of the heat engine, WHE, and it receives the temperature of high temperature reservoir is taken as TH, and there is a high amount of heat is given to the heat engine and it converts QH into WHE. So this is not possible according to the Kelvin-Planck statement. It is not possible. Then what is a possible one? The possible one is, we have a heat engine working in a cyclic process and which receives the heat from the high temperature reservoir to the and converts it into work output WHE and rejects some amount of heat into low temperature reservoir. So it receives the QH amount of heat from the high temperature reservoir and converts the part amount into WHE and rejects the part amount into low temperature. This is the possible thing according to the Kelvin-Planck statement. So this is this kind of statement is called Kelvin-Planck statement. So in real examples for any engines, we can apply this Kelvin-Planck statement. Now let us go to the Clausius statement. So before going to the Clausius statement, we can derive the efficiency of the heat engine. So efficiency of the heat engine is equal to, efficiency is nothing but output by input. So according to this possible heat engine, the output is WHE and the input is QH. So now let us derive the WHE. So WHE is nothing but QH minus QL. QH minus QL. So we can write QH minus QL divided by QH. So efficiency of the heat engine is given by 1 minus QL by QH. Otherwise, efficiency of the heat engine. So here heat and temperature are mutually convertible. So we can write TL by, so here TL is the temperature of the low temperature reservoir and TH is the temperature of the high temperature reservoir, TL by TH. So we can use this formula for deriving the efficiency of a heat engine, and this, according to the second law, this is the maximum possible efficiency given by any engine, and when we derive efficiency by formulas, it must be less than this value. If it is greater than this value, that kind of machine is not possible according to the second law of thermodynamics and according to the Kelvin-Planck statement. So this is a very important equation in second law. Now let us go to the Clausius statement. So Clausius statement can be applied to refrigerator as well as heat pump. So second statement is Clausius statement. So Clausius statement. So according to the Clausius statement, it is impossible for a device. So we can take it as refrigerator or heat pump, any device working in a cyclic process to transfer the heat from a lower temperature reservoir to the higher temperature reservoir. So it is taking heat. QL is the heat taken from here and QH is the heat given to it. So it is impossible to transfer the heat like this. So this is a impossible device according to the Clausius statement. This is impossible. Then what is possible? The possible device according to the Clausius statement is either it may be a refrigerator or it may be a heat pump So the possible device is, it is taking temperature from low temperature reservoir, that is, it is taking heat energy, QL amount of heat from lower temperature, and it is given to the higher temperature reservoir. So QH is the amount of heat given to the higher temperature reservoir by supplying some work input. When we supply some work input, this is possible. This is according to the Clausius statement. So now once again I am repeating the Clausius statement. According to the Clausius statement, it is impossible to construct a device working on a cyclic process to convert the heat from a lower temperature reservoir into higher temperature reservoir. So this is the impossible one, and the possible one is when we supply some heat input to the device, it is possible to convert the heat from a lower temperature reservoir to higher temperature reservoir. This is a proper indication of the Clausius statement. Now let us derive the COP of the refrigerator and COP of the pump. First, COP of the refrigerator is given as refrigeration effect obtained. So this is the output from the refrigerator. How much refrigeration effect is obtained to the work input. So work input is given as WN. This is the formula, and refrigeration effect is given as how much heat is removed from the refrigerator, QL divided by, and WN is nothing but QH minus QL. So otherwise we can write this is equal to TL divided by TH minus TL. Since heat and temperature are mutually convertible, so Q can be replaced by temperature, TL by TH minus TL. So this is the COP of the refrigerator formula. So this is also used in many places, and it is also used to check whether the possible devices exist in the world or not. When any inventor claims his device is correct or not, we can check using this formula. Now let us go to the COP of the heat pump. COP of the heat pump is given as the output for the heat pump is how much heat is supplied to the body, that is QH is the output, and the input is given as WN, how much work input we are giving to the heat pump. So here QH is given as WN. QH is given as WN plus QL. WN plus QL. Similarly, here this is WN. So we can write 1 plus QL by WN. So we can write 1 plus this QL by WN. QL by WN is nothing but a 1 COP of the refrigerator. So COP of the heat pump. COP of the heat pump is given as 1 plus COP of the refrigerator. This is the one formula we are getting. And another formula, COP of the heat pump. COP of the heat pump is given as, so QH, we can have it QH, and WN we can write QH minus QL. So here we can convert Q into temperature. So this is TH divided by TH minus TL. So this is a one more formula for COP of the heat pump. So COP of the heat pump can be expressed in terms of COP of the refrigerator, otherwise in terms of temperature. In terms of temperature, higher temperature divided by difference in temperature is the COP of the heat pump. So this is about the second law of thermodynamics, and second law of thermodynamics gives the proper direction for the heat flow. Heat can be flow from high temperature to the lower temperature, and there is a restriction of how much quantity is flowing in a device. Though there is some losses in a device is also possible according to the second law of thermodynamics. So this is about the second law of thermodynamics. Now let us discuss some of the problems in the second law of thermodynamics. Okay, let us now start the first problem. The first problem statement is given as a heat engine operates on a Carnot cycle between source and sink temperatures of 337 degrees Celsius and 15.7 degrees Celsius. So there is a heat engine is given which is operating between two temperatures, and if the heat engine receives 400 kilojoules of heat from the source, find the efficiency, net torque done and heat rejected to the sink. So we have to find the efficiency, net torque done and heat rejected. Now let us draw the diagram of a heat engine. So heat engine is, so now let us draw a diagram. So heat engine is given by this diagram. So we have to draw a possible heat engine according to the Kelvin-Planck statement. So which receives energy from high temperature reservoir and converts some into work output of the heat engine WHE, and rejects some heat to the low temperature reservoir. So this is at a temperature of, here it is given 337 degrees Celsius. So 337 degrees Celsius is the temperature of the high temperature reservoir, and 57 degrees Celsius is the temperature of the lower temperature reservoir. So these are the direction of heat flow, and there is some amount of heat given to the heat engine, so which is equal to 400 kilojoule of heat is given. So now let us go to the solution for this problem. The first solution required is solution. The first solution required is efficiency of the heat engine. Efficiency of the heat engine is given as, so efficiency we know the formula 1 minus TL by TH for a heat engine. So we can write the values here. 1 minus, so TL is lower temperature is 57, so we have to substitute in Kelvin only, plus 273 divided by TH is 337 plus 273. So when you substitute the values in this formula, you will be getting the value of 0.459. This is the efficiency of a heat engine. So first question is over, number 1 is over. Now let us go to the question number 2. Question number 2 is work done. They are asking for the work done. Work done by the, so work done is given by the symbol WHE. So we know the formula, efficiency of the heat engine equal to output by input. Output is nothing but how much work is done by the heat engine divided by input is nothing but how much heat is supplied. So here they are asking WHE, work done by the heat engine is given by efficiency of the heat engine into QH. So efficiency of the heat engine is 0.459 and the heat input given is 400 kilojoule. So we will be getting a value of 183.6 kilojoule is the work input we are getting. Now let us go to the problem number 3. So the problem number 3 is heat rejected. So they are asking for the how much heat is rejected. That is, they are asking for what is the QL value. Heat is rejected to the sink. So QL they are asking. So we know the formula WHE is equal to QH minus QL. So we need the value of QL. So QL equal to QH minus WHE. So here QH is 400 kilojoule minus WHE is 183.6. So we are getting the value of 216.4 kilojoule. So these are the 3 answers we are getting. So eta HE is given by this value, WHE is given by this value, and QL is given by this value. So this is the solution for this problem. Now let us go to the second problem. Okay, let us start the problem number 2. Here the problem statement is, an inventor claims to have invented a refrigerator machine operate between minus 23 degrees Celsius and 27 degrees Celsius. So this is a problem related to the refrigeration system. It is operated between two temperatures of minus 23 degrees Celsius, that is a lower temperature, and 27 degrees Celsius, it is a higher temperature. It consumes 1 kilowatt electric power and gives 21,600 kilojoule of refrigeration effect in 1 hour. So here it is given, it consumes 1 kilowatt. The input given to the refrigeration system is 1 kilowatt and the output is taken as 21,600 kilojoule per hour. This is the output. Now we comment on claim. This is a question. We have to find out whether this claim is possible or not. So now let us draw the diagram of a refrigeration system. So first one is diagram of a refrigeration system. So the diagram of refrigeration system is given us. So here it is a refrigerator. So it is operated between two temperatures. One is lower temperature reservoir and another one is higher temperature reservoir, and there is a work input is given to the refrigeration system, and the lower temperature reservoir is at minus 23 degrees Celsius and the higher temperature reservoir is 27 degrees Celsius. So these are the conditions given, and other than this there is a input given to the refrigeration system is given. So input given to the refrigeration system is given as 1 kilowatt, and the output from the refrigeration system is also given. It is 21,600 kilojoule per hour is the output we are getting. So these are the input conditions given. Now let us go to the solution for this problem. So solution for this problem is, we need to find claim is possible or not. Claim is possible or not, that we have to find. So let us now derive the COP of the refrigeration system. So which is given by the formula TL divided by TH minus TL. So now let us substitute the values. So TL is nothing but minus 23. So we have substitute in Kelvin only, plus 273 divided by TH is 37. That is, it is not 37, it is given 27 plus 273 minus again minus 23 plus 273. So these are the values we are getting. So we are getting the COP of the refrigerator as 5.0. So this is COP of the refrigerator according to the reversible conditions according to the class A statement. Now we can derive the actual COP of the refrigerator. So COP of the refrigerator actual is given as output by input. So here the output is we are having 21,6,000 kilojoule per hour. That means 21,6,000 divided by 3,600 kilowatt. So when you are dividing this one by 3,600, you are getting kilojoule per second. So kilojoule per second is nothing but a kilowatt. This is the output, and the input is given as 1 kilowatt. So into 1. So we are getting the value of 6. When you calculate this value, you are getting the value of 6. So now we will write the solution. We will write the result. So result is, the inventor claim is not possible. Inventor claim is impossible, since our COP of the refrigerant system for reversible condition according to the second law of thermodynamics is here less than. So here it is less than COP of the actual condition. So according to this reason, this claim is not possible. So this is the result here. So we can check any machines claimed by any inventor by means of second law of thermodynamics like this. So that's all about the problems today. Let us go for some other problems in our next class. Thank you.